That should be okay. Right. Okay, let's get started. Does anybody have any questions before we get started? Give the chance to sort of ask later through the presentation, but anyone with any pressing questions? No. Okay. So what we're going to do today is a really exciting area, and really starts to bring together a lot of what we've done up to now. So like it or not, we're moving into what's called a tokenization era, where we could have things like crypto tokens, crypto assets, cryptocurrency, and so on. And what we do is we pass these tokens between us, and then these tokens have some value. They might relate to an asset and so on. And it moves us truly into a digital world. So as part of this, we'll have a look at what are called ERC20 tokens. As we'll find, we can create our own crypto assets on something like the Ethereum blockchain in a trusted way. We can even create our own cryptocurrency if you wanted. And then we'll look at JSON Web Tokens. Probably you're using these just now to be able to log on to systems. So we'll look at some of the ways that these things are designed and how badly they can be used actually. Developers often are weak in terms of their JSON tokens, and it's a particular weakness in being able to steal these tokens for a certain amount of time and gain high-level access to systems. Then we'll look at a disaster area, which is OAuth 2, a standard that went from being pretty good for security in version 1 to being pretty bad in version 2. So there isn't many examples of a protocol actually going down in terms of security, but they obviously went for usability and ease of use and for development and so on, and OAuth 2 made the whole thing easy. But as we'll see, there are severe problems in using OAuth. Then we'll look at a good token to be used, and that's the Fernet token. A little bit about Peak and the Spake protocol, about to be able to prove things on either end without giving away secrets. And then finally, we'll have a look at Docker and Kubernetes, which could be used to rebuild our security infrastructures. Okay, so make sure that everybody's on mute if that's okay. And then if you have a question, just unmute yourself and please ask it at any time. Okay, so here we are. We're nearly at the end of the main presentation. So we went right through all of our foundation crypto. And as we found last week, public key is your favorite subject for many of you, which is good to see. Last week we did some future crypto, some lightweight crypto, post-quantum, and so on. So hopefully that helped you maybe select a topic for your coursework and even for your dissertation. And this week we'll do a bit more around tokenization and so on, and maybe you could even see a topic hidden inside this subject that would really excite your interest, and you could maybe take it on to your coursework or again into a dissertation. Next week is Good Friday, so I'll put the lecture online, but there'll be no live lecture at all. Okay, so we'll have a break for a couple of weeks. We'll be back in week 14. I'll set up our event next week. And then week 15 is where the coursework is actually handed in. So please send me drafts or ideas or really requests for comments and for your coursework, and I'll try and get back to you. So really try and use these weeks to be able to craft your coursework and see how you get on. Okay, so authorization and access is obviously a fundamental part of security. So if we have Bob, then Bob logs on to his local computer, and he has rights to that. Typically, you'll have some sort of admin rights to that machine. He might allow others to connect into his machine and give guest rights, or even allow others to be able to log into to his machine and use it as he would. But that becomes difficult from a security point of view, because how do we set up an infrastructure where we've got to go around possibly thousands of computers within a corporate environment and set them all up with standard rights for users to be able to log in to any computer that they actually want. So most of the time what we do is that we either set up a work group, or more typically we set up a domain. And within the domain, we authorize or authenticate the machine and also the user into the domain. And then what we have is a domain controller to be able to set the rights for the whole of the domain. So if a user has new rights, we go to one place, the domain controller, and then we can actually set up the rights for every computer within inside the domain. So in this way, it makes it easier for us to be able to set up the common rights overall. But obviously, this can be a problem, because if the domain controller goes, as you may have well found out, then you're going to struggle to be able to log in or be able to do anything without the domain controller there, as it should be, because the domain controller could be a center of attack. If someone can bring that down or makes it too busy, then no one will be able to do anything on the network. So we often have backup domain controllers. Domain controllers themselves can now run in the cloud. So we can have a cloud instance of the domain controller, and then we can have synchronized backups. But it's up to these domain controllers to be able to sync with each other. So if one domain controller gets an update, then all the other domain controllers will actually receive that update, so that one domain controller could go down and it won't cause any change of access. But the next problem that we have is that we now have lots of services that we log on to. So we might log on to a corporate intranet, we might log on to a finance system, and so on. So we have a whole bundle of things that we connect to within our corporate infrastructure. And this becomes a difficulty because we've got to log in, re-log in again to all of these systems. Okay.
Yes.
Yeah, so if you could just mute.
So I'm going to do something, drink and
Hello.
hello.
Hello. Could you just mute yourself? Please, everybody mute. Thank you. Are we all mute? Good. So the problem that we have now is how do we create a common login for each of these systems? So one way to do this is to have an authentication token. So what we do is we authenticate ourselves once to an authorization server. So we can have multi-factor authentication. We can have lots of good access control on that service. And then when we truly authenticate ourselves, we'll then be able to get a token back. And then that token can be then used to pass to all of the services which use that token. And the good thing with that is that we could have a federated system. So we could have several authorization token services that we trust. So the user doesn't have to log into our one, they could log into another one on the internet, get a token from that, and we can then trust that token for each of our services. So in this way, we get what's called one-time passwords or one-time authentication onto the whole of our infrastructure. But obviously, this Eve probably likes this type of approach, because all Eve has to do is to steal that token. If the token hasn't been designed correctly, then she might be able to grab the token. Maybe she installs a backdoor Trojan on a web browser, and whenever the token is received, she takes a copy of it and she replays it back for her session. So it improves the usability of the whole infrastructure, but obviously it opens up backdoors into the system, and where an intruder doesn't have to use any tools anymore. They'll use just a token stealing infrastructure, or if it can even be so bad that they can craft their own token if it's been badly designed. Does anybody have any questions at this point? This is our Windows domain. So most of us will connect into a Windows domain in some way. And then tools like SharePoint allow that kind of cross-domain a transfer of rights. Okay, so inside a Windows domain, each user has an SID, and that SID will show them a unique identifier across the whole world. So that will identify the domain ID inside there. In this case, we identify this as a Windows domain service and not a work group. And then at the end, it's difficult to see, we have the relative user on a machine. So the admin account starts at 500, and then all the user accounts starts at 1,000 and then moves on. So every user is then given a unique ID from there and will be unique inside the whole of the main infrastructure. There are some tools that allow you to see what your ID is and what your domain name is and what your username and identifier actually is. Okay, so what we have in our normal systems is there is in the Windows Hive, there is the place that stores all the usernames and passwords for the whole system. So this place is stored on the local machine, and obviously what someone can do is to cold boot your disk and get access to all the usernames and passwords, and then could use something like Hashcat to be able to break the Windows passwords. But if we run in a domain, then the domain controller holds all the usernames and passwords. So there isn't really anything stored on the local machine if you connect into a machine that connects onto a domain. Okay, so as we saw before, we can move towards a tokenization infrastructure where we deal with tokens, and then we can actually keep all our sensitive data behind within a tokenization infrastructure. As we saw last week, we can take a token, we put it into a processing, and then if we want to map back to any sensitive data, we can map it back within our tokenization infrastructure and make some attestations on the data. So this was the Visa best practice for tokenization, for setting up a tokenization infrastructure. We have things like strong network segmentation, so we keep our main tokenization infrastructure off the main network. We make sure that we have strong authorization in there. We have 24/7 monitoring of this infrastructure. We use good token distinguishers so that we can't confuse one token with another. The last thing we want is to take a token in and it looks a bit like another token and we end up making the wrong request for it. And we should be able to log all the transactions that happen within our tokenization infrastructure. So as we saw, that we'll have a place that we might keep sensitive credit card details and so on. Okay, so the example I gave you last week was that Bob wants to pay for something and he wants to preserve his CVV number. In this case, we get a token that preserves the privacy of that so that when the merchant gets it, they can't steal it or find it out. But that then, the token goes to the merchant acquirer. That's something like the bank for the system. They pass it on to the tokenization server. It remembers the token and then log maps it back to Bob's account and finds out if Bob has enough money to pay for this Amazon Echo. If it is, then we get a request back, a reply back, to the merchant inquirer saying that everything's fine, and then the merchant will get an attestation that that's okay, and the payment can go ahead. The good thing is that Bob can actually get a message back from the tokenization server to say that he's just bought Amazon Echo, and is it okay? So we could have a little delay in the loop while he agrees to it before the merchant actually receives back the reply. So many of the banks are now tokenizing because they see this as a good way to be able to protect users from fraud. Okay, any questions up to now? Good. Okay, so what would a token look like in terms of a future of crypto assets and so on? So one standard is the ERC20. They're not perfect from attacks, but they're certainly one of the most robust tokens around. So we can create ERC20 tokens, and if you have a cryptocurrency wallet, you'll find that you can keep your tokens inside your wallet. With Ethereum, what we have is smart contracts, and these smart contracts can actually create these tokens, and can also be used for creating cryptocurrency. For that, we can define who owns a token. So if we have an Ethereum address, we can actually define who owns it, and we can transfer tokens from one address to another. And in an instance, we can actually find out who actually owns the tokens. So let me show you some of the some tokens here. Okay, so this is just some basic code. So I've mined for some smart contract addresses on the Ethereum network, and at these places is the smart contract which created each of these crypto currencies. So inside the token, we have these functions so that we can call with an API what the total amount of cryptocurrency is, what the balance is, and we can actually approve tokens and so on. We can also have a token name. We have a symbol if it's a cryptocurrency, and we have the decimal value, which will actually define the smallest amount of the crypto currency that we have. So if we look, for example, see at the block pass one here. Okay, so we can see here, I've just got a couple of details. There's the symbol for it, that's the total supply, and this is the smart contract which created the block pass token. Okay, so each one on the Ethereum network has one of these addresses which defines the contract which made the cryptocurrency. So we could actually create our own tokenization infrastructure. So let's say that in a healthcare infrastructure, we could create a health token. And whenever we traded, we could actually just pass health tokens. And then we have a fiat currency exchange. In this case, maybe the NHS could set up a fiat currency exchange to take tokens and then to convert it back into the currency of required. But we could generally trade tokens so that we wouldn't have to involve fiat currencies at any point, and we could run things off smart contracts and make the whole thing more robust. Okay, so as I said, when you're creating a token, the things that are mandatory is the total supply of the token. So you can't create any new currency once you've actually defined the total supply, what the balance is of the cryptocurrency left, whether we can transfer from and to someone else, whether we approve whether the token is approved for its transfer, and what the allowance is on each user. The token themselves can actually, as I said, have a name, have a symbol. So we have BTC for Bitcoin and ETH for Ethereum, and so on. Okay, so so what happens is that you extend a standard Ethereum contract to be able to support our tokens. So I've taken an example here from this this article, and it creates a bear token where there are 100 billion tokens going to be in supply. Okay, so here's the Solidity contract, which creates the token. And what we see here is when we run this on the Ethereum network, we're going to create a symbol of bear token, 5 decimal places, and then that's the total number of tokens in there. So when we run this, this will then create the bear token, and we will be able to trade with this token here. We can see the standard ones, total supply, name, symbol, and decimals defined for our token. Okay, so on the Truffle development network, so you can use this if you want to implement your smart contracts in a sandboxed type environment. And we can see here, after it's been created, you can actually see that we're getting back these JSON parameters for our token. Okay, and then it could work that we actually start to define smart contracts for the provision of, say, healthcare and so on. And then whenever anything is enacted, we could define a total number of tokens in the whole of the network. And then we can actually trade those tokens. Those tokens can then be exchanged for fiat currency in the end. So when we do our trading, so for example, there's some healthcare here that's defined in a tokenized amount at a certain rate. And after something has been transacted, we can check the balance, and we can actually see that in this case, Bob has performed some care and has gained 2.5 tokens from the council. Again, Bob could trade them with someone else for something, but then could go to the fiat currency exchange, which would maybe be run by the NHS in this place, and they would have cash ready to be able to cash out, and then they would receive the tokens back again for Bob to be paid in fiat currency, and then Bob wouldn't have any more of these health tokens. Okay, the one problem with ERC20 tokens is that obviously they will reveal the owners, they will reveal the transaction and things like that. So sometimes we want to keep privacy inside a token. So we might own a work of art, say, and we have the token for that, but we actually don't want others to see that we own that. So there is now a standard being drafted called ZK, Zero Knowledge ERC20 tokens, and this will look to use zero knowledge proofs to be able to hide parts of the token so that you can still hold them and you can still prove that you are the owner, but you will be able to hide the details of it. Because the problem with Ethereum is that Ethereum is an open public network and isn't permissioned, so that anyone can look at anything across the whole of the blockchain. Okay, so there's a note provided to the ZK ERC20 token, and this is used to be able to create an extended field. It's like a little note, personal note on the token, and then that can be used to preserve the privacy of the token overall. So where do you save your tokens? Well, you don't want to save them on a web server, really. If you can, you create a hardware wallet. So the Ledger Nano S is a good wallet for storing your your wallet on it. So you need to plug in your USB, it's a USB device into the computer, and then only then can you actually access your wallet and your private keys and the tokens that you have and so on. So the Trezor is also another good wallet, and I think even has biometrics built into it. So obviously you've got to watch that somebody can get access to your USB stick. So increasingly what you have is a fingerprint that will actually authenticate the user. So you've got to watch to make sure that that fingerprint is done correctly, or you might end up not being able to get access to your cryptocurrency and tokens. And My Wallet is another one, which is an online service, and that integrates directly into your Ledger Nano device. And they say that they never store anything on their web server, but please beware that that might be possible, and that you just need someone to be able to get a web service to get access to your wallet, and then they could be taking your private keys and taking copies of things. Okay, but if in doubt, you get one of these. So this is a paper-based wallet, and basically you can delete all of your electronic methods and you end up with a paper-based one. So if you want to recover your wallet and your private keys and so on, then you basically can scan in the paper from the paper copy and recover all of your secrets. I wouldn't say this is a fallback situation. You should use probably a USB stick in a fire safe for one, and you should probably give your paper-based copy, say, to someone that you trust, or for them to store in a very secret place. So it's an alternative to the electronic methods. Okay, does anybody have any questions up to now on these tokens? No. Okay, good. Right, so let's go and look at JSON. JWT is developers just love JWT, JSON Web Tokens. So JSON Web Tokens are really a core part of many systems now. So what we have is everything is defined in a JSON format. So JSON format, just basically that it's a very simple thing. We have a name, an attribute, and then we have a value. So it's really simple. If we need to create a structure, we have what's called a YAML. YAML is a format that we can actually structure our data. But in the common form, our JSON is just an attribute name and then a value. So it makes it easy to parse and to find things. So within inside the web token, we have a header. The header basically defines the type and the basic algorithm that we're using for the token. Then it will define the payload, and the payload will have a number of attributes in there that we want to be able to pass around. So it might have the user's location, might be one of the attributes that they will use as we pass the token back and forward. We will typically define when it was issued and when it expires. Okay, so please don't issue a token that has a long a long lifetime. A typical lifetime is about an hour or say a day, because if someone gets this token, they could run wildfire for days or weeks or years even. So we typically limit the token to say an hour, to limit the amount of time that the user has authorization. When the user needs to reauthorize, they'll go back and get another token and then pass that there. Okay, so the expiration time is really important, and all systems should check for the expiry time and should not allow anything to happen if the token has expired its time. And so then finally, so this is plain text. So anybody can look at your token with a browser. I use Postman, as we'll see. Postman is a great tool. I highly recommend you, if you're dealing with RESTful web services, Postman is the place that you can actually prototype and call up a service and get things back. So in Postman, you can see the JWT token, even though it's not yours. If you've stolen it, you can still see all of the details of the token with inside there. So how do we make sure that it's credible? Then we define a signature. And the signature is going to give us the trustworthiness. So if Eve creates her own token, she could pass that to a login service and then gain access to the whole of the network from there. So we need to check the signature on it. So there are 4 main methods that we use for signing our token. Either we sign through HMAC or we sign through RSA. Does anybody want to pitch what the basic difference would be between HMAC and RSA? It's a difficult question, I appreciate, but remembering what you've done in the past, when would I use HMAC and when would I use RSA?
I think that HMAC also provides a hash of the document, while you would have to do that separately with RSA.
Could you say that again?
I said that I believe that HMAC also provides a hash of the document.
Yeah, that's true. The same thing can happen with RSA. You're signing a hash. So both will take a hash. Good answer. Thank you, Nikos. Both will give you a hash, and they will both sign it in some way. But what fundamentally is the difference? If I was making the choice between HMAC or RSA, what choices am I making? There's no silly answers, please. It's a difficult question, and you can see that maybe developers would struggle with this too. So, anyone want to pitch?
Perhaps the HMAC is to do with the signature of the calculation of the token itself, whereas if you use RSA, you maybe do some sort of signature with some communication with the target, with the communication partner. I'm not so sure.
Kinda. No, not quite. I'll open up for one more answer. What can you remember about HMAC? What is it that HMAC needs? I'll give you a clue.
Salt?
Hello, say that again?
It's salt.
Salt? No. Did you say salt?
Yes.
No, not salt.
Is it asymmetric key?
Yeah, it's something to do with that, but explain. Okay.
I believe the message is signed with a symmetric key, while with RSA it's signed with a public key. With a private key, you have to verify it with a public key.
Yeah, well done.
While in HMAC, the signer verifies it themselves when you send it back to them. So
Yeah.
the user doesn't verify the hash in HMAC?
Oh no, they do. Yeah. I mean, that's all part of it. Yeah, but good answer. Good answer. Okay, so I don't know if everyone understood what was said there. That's an excellent answer. Thanks very much. Right then, okay. So let's say we have a secret. So my secret is QWERTY123, and both the issuer and the verifier of the token knows that secret QWERTY123. So in HMAC, what will happen is that we'll use a key derivation function to be able to create a key, a secret key. I think you said there's symmetric key. That's right. We use a secret key to apply an HMAC signature. So then every token that we sign will use the same secret key and we'll actually sign it. So the weakness of that, can you tell me the weakness of that method?
For secrecy.
Yeah, that's right. Yeah, I mean, insiders will know the secret. So anyone in the company, anyone who can view the code and so on, can actually see the secret. If that's leaked, then all of your tokens will be ripped up. But they've all timed out anyway. But Eve can now create her own token, and it's perfectly valid, and it's been signed. And she could also take the tokens offline and use Hashcat to be able to go through and try to create the same signature for it. So she could take an offline token, and she could use a dictionary attack to be able to, and rules to be able to brute force, well, not brute force, a dictionary attack the token. So that's the HMAC one. So please watch when you're doing that. So what's the advantage of using the RSA one as opposed to using this HMAC one? Does anybody want to pitch in? So with the HMAC one, with the RSA one, we'll have our private key and we'll sign every token with that private key. And then now when a verifier or someone gets the token, they'll go to the public key and they'll check the signature against the token and know that it was issued by a certain entity. So in this way, we're not using a shared secret or a key derivation function. We're using public key encryption to be able to define the signature. Does everybody get that now? Kinda good. So the best method is probably the RSA method. The method that's most often used by developers is the HMAC type method. There's nothing wrong with it, but obviously once someone gets your secret, then you are in a bad place and people can run wild on your system by being able to create their own tokens that they can just easily pass to an authentication server. With things like Postman, you can craft your own JWT token and then paste that in, and you'll get automatic authorization into the whole of a domain or lots of services and so on. Okay, so what does a token actually look like in real life? Okay, so it has that header, it has the payload with attributes, and it has the signature in there for that. So if we parse out what we have, so there's the header. After that, we've got the payload in there. So that in this case, that's just that simple payload in there. And then in the end, we have our signature from them. And this is in a format that could be copied and pasted and can be passed, because you can see the letters here aren't in binary or anything like that. So in this way, we can actually gain access to our tokens. Let me see if I can find a token for you. So here is a tool called Postman, and with Postman, what we can do is that we access either through a GET or a POST, and we can pass parameters for our request and view the reply. So in this case, we're logging into this service here, and we set up like a content type. This is a URL encoded format here. This is my token that I'm going to pass to Docker to be able to log in, hopefully. And then in the authorization field, I then say bearer, and I'll paste in my token in there. Then you can't see it, but there's a send button over here, and then I press send, and then I'll get an authentication message back to say if it's 200, then I've been successful, or 4 or 5 or something, that I'm not authorized to use the system. So Postman is used a lot. Obviously, you can use Python or Node.js, and you can create your little scripts and to be able to pass tokens into the server to be able to test it and so on. But Postman is used extensively, and I highly recommend that you install it. I think it's Postman 2 is the current version. It's an amazing system for being able to pass tokens back and forward. I think I have got an online version of looking at tokens. Just give me a second while I find that for GWT tokens. Just give me a second, and just to show you. So here's GWT tokens. I'm using Node.js in this place. So for this passphrase, remember we're using a key derivation function. The key derivation function is likely to be PBKDFS2 or bcrypt or slow. And there's the attributes. This is the token that I pass, and I just showed you that token a little minute ago. That's what my parameters are. So I could say, I could generate this token here, and I can actually add in new attributes that I want, and it'll create that token for me with this passphrase. So I'm using HMAC in this place. There's the code that you have here. On the website, I've been adding in the Replit site. So if you ever want to use this, then just click here, and it'll open up the code for you there. And then you should be able to run the code on your own, hopefully. 1, 2, 3, and it should run fine for you. So Replit is a good place to kind of prototype and get things to run, but obviously you're running it mainly on your virtual machine. Okay, so that's what a good token looks like. Okay, it's not protected. Remember, you would encrypt your data at source. So if you want to protect usernames and things like that, then you would encrypt with something for your attributes, because they're not protected, because it's not that difficult for me to take that token format and then reverse engineer back the token as we've actually saw. And it's only a signature. It's not encrypting the whole token. Okay, so that's what it looks like. That's the Postman system there. Does anybody have any questions up to now? Good. Okay, so so rather than having a break, then I'll just continue on with the presentation. So for the lab today, I've set up some interesting things that I highly advise you to have a look at from there. So the lab itself, it can be a little bit challenging, but I've got some code for GWT to be able to look at the basic formats of that and to create your own JWT tokens. In this case, you're actually cracking. You can actually crack the token. So I'm giving you a token here, and I've used a 3-character passphrase. So it should be possible for you to keep trying until you find the right passphrase and so on. And then we'll go on to Fernet tokens in a little minute. A little bit on OAuth 2, but please do some Docker. We'll come on to Docker in a little minute, but it's a really important topic, and it's increasingly used in the industry along with what's called Kubernetes for workloads balancing. Okay, if no one has any questions, last chance to ask a question. I can't see the chat just now, so I don't want to reveal it. If anybody picks off a question that's in there, if you could just ask it for someone else. Nope. Good. Okay. So there's the potential of creating what's called federated identity or to be able to federate your system. So we have the concept of divorcing the service from the identity provision, and the two never have to talk to each other. So we can have a number of federated identity providers that each service trusts. So we might be logging into a healthcare system and it trusts Google to authenticate the user, or Microsoft Live. So in this case, what happens is that a user goes to the identity provider and then goes to, it's funny, my phone has just went off because I said the word Google there. The user goes to an identity provider. The identity provider checks the identity of the person, typically now using multi-factor authentication. So increasingly, say on a Microsoft type network, the user will use multi-factor authentication, their mobile phone, maybe even biometrics and so on, to be able to access to prove their identity. Once they've proven their identity, they get back a token. The token is then passed to the service provider. The service provider checks it. There doesn't have to be any linkage between the service provider and the identity provider. They can check because the signature is there, or there's a shared secret, and so on. In this way, we can actually divorce the service from the identity provision and provide some resilience. If we don't trust an identity provider anymore, then we would kick them off the network, or we can host new identity providers very quickly from that. Okay, so one of the most popular systems for authorization is OAuth 2. And with OAuth 2, what we get is an access token. So we request a token, we prove something, and then we get an access token back, and we pass that access token to the service provider. And it's very simple. Basically, we have a secret and we have an identifier. When you register for a service such as, say, GitHub, and then GitHub will provide you with your unique identifier and your secret. But anybody can create an OAuth 2, and you'll see it in Twitter and Reddit and say LinkedIn. If you want to use their APIs, then they'll give you an OAuth 2 credential, and you can create multiple ones for all the different services that you're likely to be using inside your application. So we have basically, when we register, we create an application name, we create where the website is, and then we have a callback, a redirect. Once the user is logged in, we redirect to another site. So really, the user just has to provide their identity and their secret, and they're in. So, and it's not great because if obviously someone finds these things out, maybe you've pasted it in your JS code on your GitHub and forgotten about it. Many people do this with Amazon. They'll forget that their Amazon credentials are in their JavaScript headers in their GitHub, and Trudeau just searches through their GitHub and finds the AWS login for that. So this is a pretty disastrous method, but developers love it because it's just so simple. I just need to generate two things and then that's it, you're away. No signing anything, very little credibility. It's just a shared secret that if it's found out, then you're in trouble because someone will get access to your, someone can fake the account details. Okay, so we can see here, I've got the authorization service over here. You can't see because of the video here, but we have a service provider. We go to the service provider, we get some sort of authentication, and then we provide the access. Sorry, we go to our authorization server and get an access token. The access token then gets passed to the service provider, and we can actually log into the system. That's a question. Okay, so these days it's typically web services that we're using to be able to log into systems and not the command line or anything like that. So this is an example login for GitHub. In this case, we can see here is my client ID. I've missed it off there, but anybody who's sniffing the traffic from my web browser or from my host will be able to see that. Anyone sitting at the other end can actually see it once you're out the tunnel, can actually see what my ID is, and then could be able to see the secret. And we can see here, here's the callback URL. Okay, so once you're logged in, you'll see this authorization code. Okay, so here is an example of setting up all these details to go to log in to this site here. We can see there's the client ID. So the question mark terminates the URL, and then we now get our parameters. Does anybody know how we parse the parameters? Which symbol parses?
The and symbol.
Yeah.
The and, yeah. So the ampersand will parse the parameters that we put in here, and we obviously can't use spaces. Do you know what we replace a space by?
%20.
%20, yeah. So some of the less printable URL non-safe characters are converted into %20. So you can obfuscate URLs and things like that with that. So we can see here that when we parse, the other side will take the parameters off and then parse them out like that. So we can see the client secret is sent in a kind of plain text type format inside the guest. So although we're using HTTPS, someone who's on our machine, we put backdoor, can actually listen to those requests and steal that client secret. So it's a real disaster area of a system. Okay, so there's what the token looks like in there. And you can see it's got expiry time and so on. Okay, we can obviously use curl to be able to do this from the command line and to be able to set up our token as we require. Unfortunately, it's been exposed as being pretty bad. So it went from version 1.0, which is pretty good, to version 1.0, and it dropped a whole lot of security features within its single sign-on. So this paper here outlined that more than 1 billion OAuth accounts could be breached from mobile apps because of the weaknesses in there. And they outlined that at least 41% of all the apps at the time were open to these problems with OAuth. Okay, so the way around this and the way the industry is improving this is to try and bind the TLS session to the token. So what you really want to do is that you've established a connection. Now you want to take something from the TLS connection and bind it to the token that you're actually using. And this way, someone can't steal the token and play it back, because you've got to have an authenticated access to it. So this token binding protocol here allows us to be able to take something from the TLS session and then add it, bind it into the token, and in this way we'll overcome some of the problems of passing tokens, such as replay type attacks on that. Okay, so so you can have a look at this this specification as you want. Okay, so here's an example of me registering for GitHub OAuth, and we can see here there's your name, there's the callback URL which you've got to specify, and then the home page of the URL. Okay, so once you're happy with that, you press the button, and then you will then see it will generate a unique client ID for you and a secret. So on GitHub, you can revoke all of these. So you can go back, and all of the ones you've issued in the past, if you've had a hack, you can revoke all the tokens so that it won't work with GitHub anymore. But you can also reset the tokens at any time from there. Okay, so after that you can set up your own logo and things like that for it, and that's you good to go. So then when you're authorizing, you can then pass this client ID and the client secret to this application here, and you can then be authorized. So in this way, I can use GitHub to provide a login for my site. So rather than me storing usernames and passwords, I can get the authorization to happen. Someone just has to provide their username and password for GitHub, and then I will receive a token back from GitHub to say that they've been verified, and they can get access to the site. Okay, does anybody have any questions about OAuth?
I would like to ask how you can determine what information the service gets from this token. Do they afterwards have to go ask the identity provider again, or is everything packed in the token?
No, everything's in there. All we're really doing is proving that they can log in through your identity provider. So it's not providing all the great information. JWT would be used where you want to pass attributes. All you're doing with the OAuth is at least authenticating through your identity provider, and the token you get back just means that they can log in to that
But does
provider.
So how can you get a user's name, for example, to show on the corner of your page?
Well, they'll come in. The token that you get coming back, so that when you log in, they will go. You get back lots of parameters. If it's LinkedIn, then LinkedIn provides you with a name, lots of other things. Twitter, for example, they've locked down a little bit on what comes back. There used to be lots of things that you would get back, and it breached user privacy. I think increasingly, say if you were to log into Google, you would only get your email address. and maybe the username. The user's usually got to approve the parameters that are coming back, but there's nothing to stop the identity provider providing lots of information about you. Does that answer your question?
Yeah, I think it does.
Yeah, good. I don't know if anybody uses that. I use ORCID to log in sometimes to research sites. That's my research credential. I use ORCID as an identity provider, and ORCID can pass details about my account, such as my title and my university and so on, to the identity provider. But obviously, as I said, it's increasingly that they reduce the amount of things that are passed back because of privacy issues. Right, so let's look at a good token, and a good token is a Fernet token. So the Fernet token, what we've got is a timestamp, so we know exactly when it's been created, not just that it's a stupid attribute. it's a cryptographic timestamp. We have an IV, which is a salt value, as you all know. And then we have the cipher text. Yeah, we actually have an encrypted token now. And then at the end, we've got our HMAC that we can actually sign. The good thing about this is that we can have multiple keys, and we can use what's called key rotation. So key rotation is a good thing. Because every day you could create a new key, but the other end has got to know what key that you're using. So you often have a key pool. So the key pool is that you have 365 keys, and every day that you're going to change it. And the other side also has the same pool, so that they know what's changing, so that an intruder can only discover a key for a certain amount of time before it's actually changed. So if we have a look at the token here, I've got some examples on the website. So here we are, that's my secret, hello123. I'm going to sign my HMAC, remember, it's HMAC from there. I'm going to sign it, but it's also going to be encrypted from the key value that I use with key derivation function. And this is what we get as a token back. This is the key derivation from my password to the key, and then this is the cipher that I get. When I parse it out, that's the version number. The timestamp is in here or so. Hopefully every time that I sign, I'll get a different timestamp. There's my IV that I'm adding. There's the cipher in there. My HMAC signature in there, and then when I decrypt, it gives me my thing back again. Okay, so this is the basic format that we get, but the good thing is it's encrypted in there, and if you're interested, this is the code that we're actually using for that. So we can actually pass this we can pass this around, and we can keep our messages secure from there. Okay, so it uses AES encryption, and we use a key derivation function like PDK-DFS2 to make sure we slow down the possibility of hashcat cracking the token. So then that key goes into there, and then it will create its multiples of 128 bits for the size of the token. Timestamp IV, we use this as a standard padding method if we require from that, and then we have our HMAC at the end. Okay, so there's the example that I gave. There's the hex values that we've got and that we pass for that. And so the code is there. We can create our cipher from that, and then we can pick off the cipher fields by just picking off. In Python, this is from 0 up to 2. We'll pick off the 2 characters, and then we can parse each part of the cipher string. Okay, so this method here is converting it into a hex string from, because in crypto we normally deal with byte arrays. That's 1 byte at a time. It's like in a buffer, and it's difficult for us to be able to interpret that. So we convert it into a hex string so that we can view it. Okay, so this is an example here using a key derivation function of PBKDFS2 and with a SHA-256 format there. Oh dear. Hello, sorry, I was still there.
Yeah.
Yeah, great. So, but I don't know what happened there. Just share my screen again. That. Okay, cancel. There we go. Yeah, right. Okay. So yeah. So that's it. Everybody see my screen? Is that okay? Good. Okay. So that's like the key derivation function there that we'll use to generate the key. And obviously we can use anything we want. You could use bcrypt if we wanted, but PBKDFS2 to HMAC is a good method there. So what we need to do now is to be able to pass this through like a web browser or within a URL, within a GET. So we convert it into what's called a URL safe string. So the URL safe string looks like a base64 type format and really allows us to be able to pass our data using safe characters that wouldn't be interpreted incorrectly as we pass them. So in this case, when we get our token, then our token becomes this thing in here. Okay, so when we're passing it through a web browser, it will look like that. We pass that in, and then that's then decoded or its code back into the token again, and then we can actually mine the token. Okay, so here's an example here that I'm taking a token that I've been given. I then get the key in, again, a URL safe format. So I can pass the key in this case, which is always going to be the key to decrypt this token, the token and the key, and then I can regenerate the data from there, pick up all the timestamps and so on. Okay, so as I said, a key function or an important function is key rotation, where we can actually pick off a different key from a pool, and the other side, if they have the same pool, will be able to determine the right key being used. And it confuses Eve because every day or every hour the key is changing. If she managed to crack one, then within the next hour the key has changed, and so on. She's got to go back and crack it again. Okay, so this is an example of this, where we can actually create multiple key values and then add it into Fernet, and then Fernet will automatically do our key rotation for us. Rotation means that you can go back to the start again, and then you'll rotate round. So you're probably going to be creating enough keys for a certain amount of time because they're going to come back again. Or what you can have as a strategy is that every so often you reset all the keys and you get Bob and Alice to agree back on the key pool, and then we'll go around in this way that Eve doesn't discover all the keys over time. Okay, any questions on that, on Fernet tokens? No, good. So I'm going to give you an example of a protocol that's quite interesting called PAKE, and PAKE does PAKE is an oblivious transfer of data. So let's say that Alice knows her password and Bob knows the salt value, and you don't want Alice to discover the salt, and you don't want Bob to discover the password. But in the end, they want to authenticate each other and use a shared key at the end of it. Unfortunately, in most of our systems, we store the salt and the hash value together. So if Eve gets access to the system, she just uses the salt and a dictionary and can actually derive the hash. Peak, we have a way to be able to transfer these values using what's called oblivious transfer, so that they are passed, but they're not passed in any format that could ever make them discovered. Okay, so Alice has a secret, Bob has a secret. They pass some things, and then in the end, they end up with a shared secret, or they really authenticate each other in this way. So Spake is one where we have what's called password authenticated key exchange. Alice passes something about her password. Bob passes something about his. Sorry about that. Let's go again. Okay, so they can pass secrets to each other, and then they will end up with the same key at the end of it. So in this case, in the opaque protocol, Alice has a secret. Bob has also a secret. They register initially and each other's against each other's secret, and then from there on they can authenticate each other based on that. And we use what's called oblivious transfer to be able to transfer the secrets from either side to the other side, and they end up with the same shared key and then can authenticate each other. So in this way, we overcome the problem with HTTPS, which is only authenticating one side. We want to authenticate both sides, but we don't want to give away the secrets from them. As a last topic, we're going to have a look at Docker. Docker is a very important topic to look at. So you've got to wonder, why do we need servers? So why do we set up these big verbose servers running SSH and login and every service under the sun? We end up with big verbose servers that are doing lots, but we don't only use them for a web server and so on. So the Docker methodology is, why don't we just break these out into little components and then allow them to exist in a common infrastructure driven by software, and then the components can all integrate with each other. And this gives us the concept of Dockerization, in that we can have an infrastructure which dynamically brings in these Docker components, are made for manufacture, are almost like customized. So they're generic, we make them customized, and then we push them out. As more people log into the system, we need more of these servers running, so we'll take more and we'll push them out. And then we need what's called a workload management system to be able to manage the workload between these components. If we're dealing with logins, then we might share the logins into 3 different login servers, so that each of them has a fair load. And then when it's light, we might kill off some of the Docker components, so we only end up with, say, 1, and then that will cost us less in terms of our cloud resources. Okay, so Docker is a way that we can actually set up our applications in a much more dynamic infrastructure, more lightweight, and to break down our kind of application to smaller components. The bit you're not seeing at the end is Kubernetes, and Kubernetes is used to manage the workload so that it can know how much work's going on, and it can create new Docker components to cope with the work, or it can delete them. It finds out if a Docker component has crashed, and it will get rid of it, and it will bring in another one to replace it. So Kubernetes is a really interesting area, but you'll see areas like Puppet and so on. That whole orchestration of work is a big area, because in the cloud you pay as you go, and the more you consume, the more servers you run, the more it costs you, and so on. Okay, so this is what it looks like. So here is our virtual machine. We sit with a hypervisor, and then we build all our sort of virtualization on top of that hypervisor. In a Docker type environment, we have the Docker engine, which is running, and the Docker engine will then do things like networking, tasks, and so on. And it will allow all our Docker components to interconnect into our system. And we can even run our Docker infrastructure on a hypervisor to be able to run it on a Windows machine or whatever, even a mobile phone if we wanted. Okay, so this is how Kubernetes runs. Kubernetes, we have an infrastructure which can manage the load and then allow Docker components to be run up whenever required. So the great advantage with Docker is that we can take a customized instance. In this case, it's an SSH server. So rather than us buying a Ubuntu or a Windows server and the whole box, it's much easier for us just to create a Docker component which is generic as to running an SSH service, and then we will customize it. So we run some scripts to be able to install it. Then we can put passwords and usernames onto that Docker component, and then we can actually push that out. So this is the basic config file for a Docker component, and it's, in this case, we're setting up SSH onto it. And I think in the lab, I'll show you what we're going to build in the lab. Hopefully you can get this running. So I highly advise you to go to the end of the lab quite soon and get this set up. Okay, so it's really easy on a Mac, Windows, or Ubuntu to install your Docker infrastructure on there. Once you've created it, as I said, you create your Docker file. The Docker file then runs, and it will actually create your Docker instance for you. Once you build it, and it's ready to go as an instance. And we use things like Docker image ls to be able to see all the Docker images that we're actually running at any given time. And you should find that they don't take up much space. So it's only using nearly 200 megabytes, where if we ran a Windows server, it would be taking 4 gig and so on. Then when we run it, we can give it a name. So we can have multiple SSH servers in this case. And then what we do is we can map the port. So one of the customization for SSH, say, is the port that's going to run on. It doesn't have to run on port 22. We could run it on port 32769. So when we run the component, we can actually set up the Docker instance to be able to map to a certain port in there. Okay, so we can list it running and so on. And then there is a format called YAML, yet another markup language that allows us to be able to customize the instance, to be able to set up usernames and so on. It gives us more structure to the system that we're actually using. So in this case, I'm setting up usernames and passwords and so on onto the Docker component. Oops. And so we just go there, and that's it. Does anybody have any questions at all on what we've covered? No. Just let me check the time that we have. Okay, so we've got good amount of time left. So what I'd like to do is to go to our little test. So if you've got time, we'll see if we can get our test running. There. Okay, so if you can connect in, 821.6709. Good, got one person at least. Anybody, any questions on what we've covered before we start the test? Okay, and most people connected. Good. Okay, so you just keep trying. I think the ID appears. So I'll just do a quick survey again about what your topic is for your coursework. Lightweight crypto, a little bit of blockchain, some good zero knowledge proofs. Oh, quite a lot of blockchain. That's excellent. Good. You can create your own cryptocurrency. Some for post-quantum crypto, and I obviously didn't manage to sell tokens that well. But then maybe you can do some tokens and blockchain together. And then, okay, a nice split there. Nobody's into homomorphic encryption, and nobody's into. Oh, good. We've got a tokenization one. Yeah, good. Right then, so we'll go into our little test. So we'll see what you remembered from this session. Sorry about the music.
It's pretty good.
Okay, everybody. I didn't realize the music would go on. Okay, so for Visa best practice on tokenization, which is not a feature. I'll get rid of the music. Okay, so it was low latency times, network segmentation, really important, strong authorization, 24/7 monitoring, logging of transactions is really important, and strong token distinguishers is really important. So low latency, yeah, you want that, but actually security is more important. So so that's the one feature that's it's not really required. Okay, so we'll just see. Not Bob did quite well there. We've got 6 people getting that one right. Good. Okay, so we'll try the next one. Okay. In a Windows domain, which is the relative user ID, RID, and that 15211056. What's the user ID in there? That's user ID is the last part. This part is the domain name part. It's the username start at 1,000 and go up. The admin account is 500. Okay, quite a good spread of marks there. Glass Spider, Top, Pingu, and Not Bob. ET was the fastest in that one. Okay, what's the domain identifier in there? the domain identifier in there for the unique domain that you're creating for that. As we say, that's user name. So Bob, not Bob, Bobcat did well there. Pingu might be top. Yeah, Pingu's top. Glass Spider, not Bob. Quite a long tail here developing. Which allows for the creation of cryptocurrencies. ERC20, miners, proof of work agents, or cryptocurrency exchanges. If we want to create our own cryptocurrency, which one would we create? ECR20 tokens. Here we go on. Satoshi is doing well. It's good to see. But it's Glass Spider back at the top again, which is not mandatory. A mandatory function supported in an ERC20 token. Delete, total supply, balance, transfer, allowance. Well done. There's no delete, of course. Okay, there's a total supply of the tokens, there's a balance of it. We can, that should be say transfer, and there's also an allowance function, but no delete function on an ERC20 token. It's an interesting area if you're looking for it to look at law enforcement investigations of ERC tokens, because you can actually trace them across the blockchain. So it's Pingu back at the top there. Well done. Which is not part of a JSON or a GWT, a JSON Web Token, header, payload, signature, or public key. Public key is a header, a payload, a signature, and there's no public key. We obviously need to get that in some other way, such as from a certificate. Okay, a lot of people did well there. It's still Pingu, top, ET, Glass Spider, not Bob. It's bobbing around in the top there. An JSON token, what defines the credibility of the token? The signature, the name of the token, the header details, or the payload JSON parameters, that should say. What defines the basic credibility that it really is a valid token? It's his signature. Signature will define basically whether it is a correct token or not. Okay. Still Pingu. Settling down a little bit. Up at the top. GWT uses HMAC SHA-256, which is true. We have a secret for all tokens and sign with the HMAC. We have a private key for all tokens and sign with the HMAC. We have a public key with all tokens and sign with the HMAC. We have a random value. If you get this one, you're doing well. Okay, we have a secret for all tokens, and then we sign for the HMAC as we saw. So we don't have a private key because that's for RSA. We use a public key, that's for RSA. And a random value, we don't use a random value, we use a passphrase to generate the key. Okay, let's see if that changed anything. Trent did well there. Pingu didn't do so well. I know it was rather quick, but ET is top now. Nice linear grades there. What type of token can be easily bypassed? GWT, Fernet, OAuth 2, or ERC20. It's OAuth 2, a disaster area of a token, but simple, and developers like it that way. So, so please beware of OAuth 2, and perhaps move towards GWT, properly signed GWT, or a better token than that. Okay, not Bob did well there. Not Bob, and Glass Spider, maybe Glass Spider top. And not Bob, ET falls a bit. Trent was the fastest there. And Satoshi is still not able to get into the top 5. A method for passing tokens into web infrastructure is URL safe format, HTML, CSS, or hex format. It's URL. We don't convert into hex, we convert into URL format and then convert that back again. Okay, so let's see how we're getting on. And this Liskov Lamport is doing well, moving up all the time. And Trent not so well. Not Bob is top now. With Fernet tokens, which helps reduce the risk of an intruder gaining a secret key. Signatures, hash values, token expiry dates, or key rotation. Key rotation. Okay, so still not Bob, doing well there. Changes that a little bit, and it's not Bob. So who's not Bob?
That was me, Jamie.
Do you want to unmute yourself? Oh, I'm a mute.
Hello?
Who's not Bob?
Jamie. Jamie, can you hear me?
Yeah, I can hear you.
Yeah, okay, cool.
So I think I've got that music playing in the background. Sorry, who's not Bob?
Jamie.
All right, good. Thanks for that. I had my microphone, my headphones turned down a little bit. Okay, thanks for that. Does anybody have any questions at all? Nope. If somebody could look at the chat, so I'm not going to pull up the chat just now. Is there any questions in the chat that I'm missing that maybe someone could outline? As I'm recording my screen, so I'll probably just stop recording my screen. So what will happen after this is that we'll have a little break, and I'll stay online in this session. And I'll be here if you have any questions about the actual lab. Is there any questions? Okay, just let me stop sharing my screen, and then I'll stop recording.